The next and last memory function that we're going to be focusing on for now is called AlignedAlloc. What this is going to do is return a memory segment that's aligned to a specific memory alignment. This can be useful for any number of things. So to get started, we need to declare a new struct and we need to call it AlignedMemorySegmentHeader. The only thing that this will contain is a 64-bit address, and we're going to use one of those bits as a boolean. So we'll do a uint64 memory segment header address 63. So that's a colon, not a semicolon. And then we have a bool is aligned colon 1 semicolon. This needs to be 63, not 64, sorry. So basically what this does is points to the memory segment header of the aligned memory that we just allocated. And this lets us use align allocate with our standard free function and not have to design a new align free function. We're making this bool is aligned as 1 bit, so we're setting the most significant bit as 1, and we're doing that so that the free function can recognize what a aligned memory segment header is, because in a normal segment header it won't be 1 because, well, we're not going to be working in the trillions of bytes range, because that will be absolutely insane. So to get started, we need to create our new function declaration, AlignedAlloc, and this takes 2 parameters, the alignment and the size. So uint64 alignment and uint64 size. Alright, so let's copy that into heap.cpp. We can close all these away so that we don't have to look at them. And we can start creating our function. Alright, so first we need to make sure everything is aligned to 8 bytes. So uint64 alignment remainder equals alignment modulo 8 alignment minus equals alignment remainder I should say. If alignment remainder does not equal 0, alignment plus equal 8. And we need to do the same with size as well, so we can just copy this, paste that, and then replace alignment with size. So we have size remainder equals size modulo 8, size minus equal alignment remainder. No, that needs to be size remainder. And if size remainder does not equal 0, size plus equal 8. Alright, now we need to calculate the full size. So basically what we're going to do is allocate a memory block of size alignment plus size, and this will allow us to move our returned value around inside of this new memory block and not have to worry about an overflow, so we can generate the aligned memory block as we need to. This is going to waste memory on the size of alignment, so just be mindful of that. It's not going to be a really big deal because computers these days have gigabytes of memory, but for simplicity we're just going to be wasting a little bit of memory. So full size equals size plus alignment. Alright, now we need to use malloc to allocate a value. So malloc val equals malloc full size. And we can get the address by doing uint64 address equals uint64 malloc val. So now what we need to do is align the address along the alignment. So what we need to do is get the remainder. So the uint64 remainder equals address modulo alignment. And then we can do address minus equals alignment. Now if remainder does not equal 0, we need to do a few things. We need to first add address plus equals alignment. And now this is where our aligned memory segment headers are coming into play, because if remainder equals 0, then we can just use the malloc block for the free function. But if not, we need to create a new aligned memory segment header. So aligned memory segment header AMSH equals new aligned memory segment header of the address -1. AMSH is aligned equals true. And we need to set the memory segment header address to the malloc val. So uint64 malloc val minus the size of memory segment header. Now we can return void pointer address. Address needs to take remainder, not alignment. I made a mistake. This is aligned. It needs to be memory segment header address. So that was a little bit to take in. I probably didn't explain it the best I could. So basically what we're doing is making sure our alignment and our size is aligned on 8 bytes just to keep everything in order. And then we're getting our malloc value using malloc, calculating the aligned address, and if we need to, we're adding in the aligned memory segment header so that our free function knows where the memory segment header is. So now we can test this out. So we'll go back to kernel.cpp, get rid of this stuff, keep test address. We can use aligned allocate, and let's align it say over 4000. So now we can print string hex to string uint 64 test address. Alright, now let's see what we get. Alright, so as you can see, we've returned a memory location that is 104000. It is aligned to a 4000 byte boundary. Now we can push it along even further. If we malloc something of size 4000, it's not going to go directly after this malloc, it's going to go at 8000. Let's see. There we go. So it's correctly aligned across a 4000 byte boundary. Perfect. But now we need to work on the free function. It's a simple modification to get free to work with our new aligned allocate function. So we need to get current memory segment equals this, and we'll just declare this on its own up here and set it down here. And we need to do aligned memory segment header pointer AMSH equals aligned memory segment header pointer address -1 if AMSH is aligned, current memory segment equals AMSH memory segment header address converted to a uint 64. Oh yeah, and converted to a memory segment header pointer. Alright, and we need to encapsulate this one inside of a else. There we go. So we are getting the aligned memory segment header, the address of where it is, and if it's aligned, then it equals the memory segment header address that is inside of the aligned memory segment header. If not, we're doing what we normally do. Now we can try and free it and see what we get. So get rid of this malloc call, and now we can free test address. And now we'll put in a new print string just to get to a new line. So return and new. We can calculate a new test address, which we can just do a standard malloc of size 4000, and we can print that. So test address 2. Let's see what we get while we're freeing test address. Alright, so now as you can see, we're aligning allocating to 4000, freeing it, and then putting in our new malloc. But if we remove this free call, then our malloc is going to go after the aligned alloc call. Here we go, directly after it. There's one more small change we need to make before we're finished, and that's we need to change the realloc function. At the moment, the realloc function will crash if we use it on an address that was returned by aligned alloc, so we need to fix that. And to fix that, we can just copy our little thing that we've got down here in free from current memory segment to the end of the else statement and replace everything with old segment header in the realloc function. So current memory segment now equals old segment header, and we can get rid of this declaration here. Now realloc will work with aligned alloc as well. It won't reallocate it in an aligned sense, but at least it won't crash. Okay, so that will be it for this video. As always, thank you for watching, and I will see you next time.